Hi, my name is Adrian Popielas, and I'm a mechanical designer here at ClearPath Robotics. And today, I'm excited to announce Turtlebot 4, the next generation of the world's most popular open-source robotics platform. The Turtlebot 4 aims to build on the success of previous versions by offering robotics researchers, developers, and educators a fully capable ROS2 platform with better sensors, more computing power, and an exceptional user experience, all at an affordable price point. The mobile base of the Turtlebot 4 is built on the iRobot Create 3 educational robot, which provides an IMU, optical floor tracking sensor, and wheel encoders for accurate positioning and localization. It also includes a suite of sensors including infrared, cliff, bump, and slip detection, along with a 26 watt-hour lithium-ion battery for powering additional sensors and accessories. All onboard sensor data are available as ROS topics via the network-connected ROS2 API. The mobile base provides a payload capacity of 9 kilograms and is capable of driving continuously at speeds of up to 0.30 meters per second, with the safety system engaged, and peak to 0.46 meters per second in override mode. Fully integrated with the mobile base is a Raspberry Pi 4 computer running Ubuntu 20.04. ROS2 and onboard sensor drivers. Integrated with the onboard computer is a front-facing stereo camera and a 2D LiDAR, allowing users to get started quickly with SLAM and AI-based applications right out of the box. Additional sensors and accessories can be easily integrated with the system using an accessible, powered USB hub and the top mounting plate with uniform mounting holes. A programmable LCD screen allows developers to display information from any of the ROS topics. The platform's IP address is also displayed, allowing users to quickly connect via Wi-Fi to the robot. Turtlebot 4 will ship with an Ignition Gazebo simulation model, allowing users to develop applications and test their code in a simulation environment before deploying to the real robot. As with all ClearPath platforms, the robot will ship with ROS pre-installed and configured, along with detailed user documentation, sample code, and a variety of tutorials so users can get up and running quickly. Turtlebot 4 will be available in spring 2022. To sign up for updates and pre-order notifications, visit www.clearpathrobotics.com/turtlebot.
Hi everyone, I'm David from Bolina, and although we weren't quite ready to submit a deep dive into our new robotics platform this year, by next year, we'll be ready and we'll be back with a full, proper presentation on the new base platform architecture for robotics projects that we're building. But in the meantime, Christian is going to give you a sneak preview of what we're up to. Oh, and you can follow along on our forums where Christian goes into detail as he iterates on the design and gives the thought process behind his hardware selections. So definitely check out forums.bolina.io and click on Show and Tell. Now, here's Christian.
To help us integrate ROS with the fleet management system we work on here at Bolina, we've built a so-called default robot. This is a €350 platform decked out with all the sensors we could fit. So here we have three sensors, IR, time of flight for obstacle avoidance. There's a LiDAR for 2D mapping and navigation, a RealSense camera. Processing is done by the Jetson Nano, the 2GB version, and the system is all powered by USB power bank. One of the most important things was to make this platform as extendable as possible. So that's why we added these lines here, which help you either run wires through or connect things, which it wasn't designed at the beginning. For example, here we have added an IMU to add precision to the SLAM algorithms by just using a screw and routing the wires through here.
Hello, my name is Benoit. I'm a PhD student at Tonera and ISAE Super and I will present Corail, which is a project that aims to allow Gaussian programming using ROS2. So here is a simple example with two tasks in the ROS2 implementation. And we can see that in theory, all deadlines should be respected, but that actually this is not the case. And this is because there is no synchronization, there is no preemption, and there is no priority in ROS2. And so we can't make hard real-time programming using only Rust2 and RCLCPP. And this is why we use the executors to implement Korai, which has an API really similar to RCLCPP with just some parameters to add to some functions. And we can see that with the Korai, the actual timeline is very similar to the theoretical one. So you can make hard real-time programming using Korai. And if you want more information, you can go to the Korai website or send me an email, and I will be very happy to answer your questions. Thank you.
Hi, my name is Justin Kearns. I'm a robotics engineer at iRobot, and I'm here today to announce Create 3. Create 3 is the next generation of our Create robots. It runs ROS2 natively and exposes topics and actions through both Wi-Fi and USB interfaces. In addition to the standard proximity sensors from previous Creates, it has an IMU and mouse sensor providing more accurate odometry. The ROS2 API provides publications for all of the sensors on the robot, including using standard messages where available. That includes the ODOM-based link transform and the ODOM topic, as well as taking commands through the command bell topic. This makes it compatible with standard libraries like Slam Toolbox and the Nav2 stack out of the box. It additionally offers actions for some behaviors that do tight servoing against the sensor data, such as docking and wall follow. In addition to the robot, we are releasing a simulator that has the same API. This gives the ability to write applications against the sim that can be used with the robot with the same code. The robot exposes power and data over USB-C, as well as a separate battery voltage connection for powering payloads. The USB-C connection can be used, for example, to power a Raspberry Pi 4 and subscribe to the robot's topics over Ethernet through USB. Mechanically, the robot has a detachable faceplate with a uniform hole pattern to mount payloads. The bin of the robot is also empty with a mount plate for compute or additional peripherals. The iRobot education team is excited to bring a low-cost, capable platform to market to help further bring ROS2 into academia. We are looking forward to engaging with the academic community for educational uses of this platform. In addition to educational uses, this is a capable base platform for more advanced prototypes. Here are a couple of internal projects we have done with the platform, using RP LiDAR and the Raspberry Pi 4 for autonomous exploration, and using RealSense for 3D mapping. The robot will be available to ship starting April 2022. We are releasing the simulator today for you to download and start writing applications against. We invite you to visit edu.irobot.com/create3 to learn more, ask questions, or apply to become a beta tester. Thank you for your time.
Webots is a modern robot simulator, natively supported on all major platforms and distributed as Snap, Brew, apt, Tarball, and Docker. It comes with a large library of well-calibrated sensors, actuators, and robots, including wheel robots, legged robots, drones, industrial robots, and automobiles. You can easily create your own components using the built-in graphical editor. Thanks to the support of the ROSIN and OpenDI European projects, we invested a lot of effort in ROS2 integration. Our recently introduced Webots ROS2 driver automatically exposes an interface for many devices like cameras, LiDARs, or GPS. Moreover, you can easily extend the interface with custom C++ and Python plugins, or use pre-made one like ROS2 control. We provide a lot of examples using this new interface, with SLAM, with Navigation 2, with MoveIt 2, with ROS2 controllers, with a command interface, with physical robots, with continuous integration. Try now to create your own Webots ROS2 applications. And do remember, failure doesn't exist.
Hi everyone, my name is Dira, and I'm going to be talking today about two visualization tools I wrote for ROS. Both of them support both ROS 1 and ROS 2. So here I have a list of ROS topics, and let's say I want to, imagine this is a real robot, but it's a ROS bag, but same idea. Now let's say I want to view this camera topic. A lot of people might just type ROS topic echo, see a bunch of junk on the screen, and determine their camera works. But there's a better way. If you use ROS show, you can actually just view the camera right in the terminal. So you can actually do this from halfway around the world, SSH'd into a robot. So this is really awesome because you don't have to worry about port cords and things. And ROS show also works on LiDAR scans, GPS fixes, odometry, time series data, voltages, and standard messages, lots of other things. Now here's another tool I wrote, which is ROS board. ROS board runs as a ROS node, and it spins up a web server on your robot. So all you have to do is go to your robot's IP, port 8888, and you get a list of ROS topics. So check this out. All I have to do is click on some of these topics, and I can view them streamed right into the web browser. And for example, images, LiDAR scans here, even Velodyne point clouds. So I hope a lot of people find this useful. By the way, ROS Board is designed to be mobile friendly, so you can walk around with this with your robot and view ROS topics, right from your phone. So I hope people find this useful, and also just to know, both of these tools, ROS and ROS Board, both support both ROS 1 and ROS 2. You can get them at github.com/dira/ROSShow and ROS Board. The URLs are up here, and please try them out, build on them, give me feedback, and hope we can build some better visualization tools for ROS. Thanks everyone, and have a great day.
Hey, this is Felix, and I want to show off a fun thing that we did. We made our robot arms play Diablo, the juggling toy that you see in this video. We already published an IQA paper, so you can check out the details there. But for ROS World, we are publishing this code, so you can play with this now and extend it. In the video, you see some of the motions that we implemented, like throwing and accelerating the Diablo. But what else can you expect to do with this package? First of all, you can visualize the Diablo and the string and control the robot arms playing with it. Here you can see the Diablo and the red bubble around it, and this bubble defines the places where the Diablo can be when the string is taut. Did you know that those places are actually defined by an ellipsoid mathematically? Yeah, it's cool stuff, and you can read all about that in our paper. Next, you can simulate the Diablo in Gazebo, so you can run all of this in simulation and plan motions to make the Diablo move a certain way, like the circular motion or throwing. Optimizing those motions is also part of the code. Next, we really want this to be a machine learning tool, so we included a dataset of human demonstrations, which you can use to teach your robot how to juggle a Diablo. You can find all of the code on this GitHub repository, so you go have fun with it and play some Diablo with your robots. Finally, this was all part of an internship at Omron Sonic by this dashing young man, and can you believe it, we are hiring. So if you want to work in Tokyo and publish cool robot stuff, open source, we have a place for you. So hit us up, we really need robot people. Thanks for listening.
Hello ROS World, I'm Pedro Arias, member of JD Robot and developer of JD Robot's Drone Stack. JD Robot's Drone Stack is an open source ROS-based package that provides a bunch of methods to simplify the development of drone applications. It's designed as a wrapper around the drone, allowed to build drone applications for getting the drone moving. It supports different reactive behaviors as speed control, position control, or mixed control. These controls allow us to create drone vision-based applications, and some examples will be given in the next slides. The drone stack uses ROS and MapLink within MapROS, typically used in most common autopilots as PX4 or Autopilot Omega. Besides, we want to show you some of the API methods which allow different reactive control methods. Several drones are supported. This slide illustrates simulated PX4 and a real Telodrone, both running the same RQT app to manage some operation as taking off or landing. As explained before, one of our goals is to simplify application development. We show you two applications that we have built. The first one, Follow Color, shows the Telodrone following a colored target. Follow Color is as simple as a color filter, since Drone Stack reduces all the complexity in the control. The second one, Robotics Academy, is a framework to learn computer vision and robotics, and also to learn about drones, where our Drone Stack API is offered to the student to code the drone behavior. Thanks for listening, and feel free to use or contribute in our JD Robots Drone Stack. Bye.
Ever wanted to run ROS2 over email? Yes? Introducing RMW email. And here's a demo.
eProxima FastDDS Monitor is a graphical tool designed to track the state of DDS networks deployed with the eProxima FastDDS library, allowing users to visualize key metrics such as latency or throughput with just a few clicks. FastDDS Monitor seamlessly integrates with the ROS2 framework when using FastDDS as its backend for communications. In this video, we will demonstrate how to monitor the state of a ROS2 network. Before starting, make sure that you're using the ROS2 Galactic version or above, and check that the FastDDS statistic compilation flag is on when building the library. Right after that, we set the list of statistic data we want the nodes to publish through this environment variable, and we export an additional variable to use FastDDS as middleware on ROS2. Now we can run a talker and a listener. And knowing the communication has been established, we're ready to monitor the network. Let's check the performance of our DDS network on ROS2. First, launch the application and select the DDS domain ID to monitor, in our case, the domain 1. Let's now create a new chart and start plotting statistic data in real time. I will first inspect the latency between our talker and listener. We need to select the corresponding data writer and reader, and choose the desired statistical measurements to plot. I will go for mean, standard deviation and minimum values. We can now look at the graph and further inspect any region of interest. For example, this peak in the latency plot might be an indicator of network congestion, and knowing the precise time of its occurrence can give us very valuable information when investigating the cause of the issue. And this is how you can monitor the state of a ROS2 network deployed with FastDDS. And don't forget to take control of your performance with FastDDS Monitor.
Transitive Robotics offers full-stack robotic software capabilities on an open core platform. All you need to do to start using Transitive is to run the curl command from your fleet page. Once installed, your robot shows up on your dashboard and you can start installing capabilities. We'll use WebRTC-based low-latency video streaming for this demo. Unlike other fleet management solutions in the market, Transitive capabilities are installed and sold separately, with many of them being free. Once installed, you can configure the capability by choosing a video source. When you are satisfied, you can use the provided HTML in the embedding instructions to embed this video widget in your own web application or any other web page. To request an invite to our beta program, please email support@transitiverobotics.com or reach out and I'd be happy to chat.
Hi, my name is Ben Greenberg, and here at Southwest Research Institute we're developing a proactive human-robot co-working space. We're doing this because we want robots and humans to be able to work safely and efficiently in the same area while fully leveraging the capabilities of both of them. Take, for example, a robot moving something from a shelf to a table where a person's going to need to work on it. When the person's at a safe distance, that's fine. The robot can go through its planned motion. However, when the person approaches the table to do their work, all of a sudden this trajectory is going to collide with them.
What we're doing is giving the robot the ability to anticipate this collision and then change its motion on the fly so that the work is completed but a collision is avoided. We're doing this by using a markerless motion capture system which runs off of 2 simple 2D cameras, and we have a real-time robot motion planner running in the background to generate the motion. The markerless motion capture system is able to run in real time and produce 3D positions for all the joint centers, which are then fed into the robot motion planning pipeline. We're leveraging the Tesseract and TrajOp libraries to iteratively solve this motion planning problem. And you can see here how as this person's model moves, the trajectory which we're seeing visualized in each frame here is able to recoil as the person comes closer to being in collision with it. We're hoping to use this work in the future to improve the study of how people behave in this system, as well as adding new capabilities to the robot, like being able to predict where a person is going to be. Additionally, we're planning to deploy this in the field for picking, kitting, sorting, and other sorts of applications.
Hey, I'm Thierry Villageois from MISLab Polytechnique Montréal, and let me show you our awesome space project that would not have been possible without the amazing ROS community. The goal of the project was to build a team of autonomous robots to explore planetary analog environments. Our software stack contains a mix of custom and community-built ROS packages, and we are leveraging the awesome ROS2 features to get a robust communication and coordination between the robots. We even streamed the robot maps from the Canadian Space Agency's Mars yard back to our lab in real time using ROS2. Those maps were then shown in VR to our remote human operator for monitoring. If you want to know more about this project and our codebase, check out those links.
Hi ROS community, Aaron Griffiths here. Thank you to you all for all your efforts with ROS, and thank you to ROS World for letting us showcase our newest product, ROS in the Box. As the engineering manager at Enjoy Robotics, I couldn't be more enthusiastic to showcase this new product. Happy ROS World, and see you next year in person.
Introducing In Situ, a ROS visualization package for creating rich task overlays developed at the University of Texas at Austin. At its core, In Situ overlays ROS image streams with filters to provide relevant information, such as system resource usage, end effector gripping range, or data from environmental sensors. The main GUI features convenient resizing and repositioning controls and provides save and restore functionality so users can get up and running in a snap. Users who find that their use case is not covered by existing filters can create their own using C++. The included boilerplate generating script will get new users coding in under a minute. Check out our GitHub page for more information, and feel free to reach out with questions or suggestions.
Hi everyone, I completed my Google Summer of Code at Cherry Robot. First, let's look at the problem that Cherry Robot tries to address. There exists a high learning curve in robotics, and beginners are bogged down by software and hardware dependencies before being able to implement algorithms. The Robotics Academy by Cherry Robot is built on ROS, Gazebo, Docker, and Django. It hosts a variety of challenges across drones, navigation, exploration, and vision principles. Here is a demo of the interface. During the Google Summer of Code, we ported the platform to ROS 2. One significant addition was the ROS 2 web template. Here is a demo of the pick and delivery exercise that we implemented during GSOC. In this exercise, the user can learn about nav2 and behavior trees. For more information, please feel free to visit our project website, Contributions.
Hello ROS World 2021, my name's Keegan Neve of Neve Engineering, and this is our robot NE5. NE5 is a full-featured open-source robotics platform. The robot features stereo cameras, 2 IMUs, one in the head and one in the base, 2 7-degree of freedom arms with grippers, and all built upon a tracked base. So, how can you get involved? All of the CAD models, the code, the documentation required to build this robot are available on our GitHub page. Not only are the code and the files available for the physical robot, we've also got a gazebo simulation available on there too. We've shown you a bit of the robot and what it can do for you. Now, here's what we're asking for you to do for us. Use it. All of the CAD and all of the models are available for you to build this robot yourselves and to take full advantage of. All we ask is that you provide feedback and any pull requests for any improvements or changes you've made that may benefit the rest of the community. If you're interested in learning more about the develop of this robot, you can actually find the history of it on our YouTube channel. You can also see demos of the latest version of it, this being filmed a month before ROS World, so who knows what's happened since. If you're able to help out financially, we also have a Patreon. All of the money that goes into the Patreon helps us develop this robot further and the other robots we have in the works, and every single penny helps. So if you're able to, please do support us over there. If not, follow the channel, star us on GitHub, and hope to see you around. Bye for now.
Pupper can use a single camera sensor to detect objects. It also supports OpenCV's official 3D camera module. You can make lots of interesting projects. Mini Pupper can map its environment and learn in real time from things around using its LiDAR and camera sensor. With the map, Mini Pupper can answer, "Where am I? Where am I going?" You can call it self-driving technology. Mini Pupper can make robotics easier for makers, hackers, schools, homeschool families, enthusiasts, and beyond. Not limited to hopping, trotting, and running around, but can also do something different. It has everything you need to actually accomplish your mission.
Hello, my name is Cora Moreno. I'm a doctoral student in ocean engineering from the Center for Coastal and Ocean Mapping at the University of New Hampshire. I'm interested in training a deep reinforcement learning agent to navigate an unmanned surface vehicle, which is basically a self-driving boat based on sensory data as an input. So for that, I used RobotGym, which allows to interface ROS-based robots, whether they are simulated or real, with OpenAI Gym. For the simulation, I used a simulation from the Virtual Ocean Robot Challenge that took place in December 2020, and I wrapped that as an OpenAI Gym environment, which is then I used to train the RL agent. The observations of the environment are composed of the target location, the boat speed, and the detected landmarks. The action space includes 4 discrete actions that are then translated into linear and angular velocities. and reward function assigns rewards based on target navigation, visual navigation, and the reason for termination, which can be collision, leaving the workspace, reaching the maximum allowed time steps, or reaching the target. Here is a demonstration of different possible episodes, whether it's successful or failing due to getting outside of workspace or collision. Thank you so much for listening. If you're interested in more information, please reach me out through email or through my GitHub account. Thank you so much.
We are Nobleo Technology. In the last years, we have been active developing high-quality autonomy solutions for several industrial applications. We are happy to present you our path tracking PID module, which offers proven high-performance path tracking for industrial robots. The main features of our module are tracking the path with the base link instead of just following a carrot ahead, open-loop forward-backwards velocity generation, angular velocity feed-forward control for improved performance, support of front-steered robots which exhibit tricycle kinematics, velocity regulation based on nearby obstacles, and based on predictions to keep the tracking error bounded. We have proven the performance of this module in 2 industrial robots. This pallet truck uses the model predictive control feature. The forward velocity is reduced whenever the tracking error is predicted to be larger than a desired threshold, allowing the robot more time to steer. As a result, the truck accurately follows the global path despite the sharp turns. The module also supports reversing maneuvers needed in applications that require high accuracy, like pallet picking. Hope you also get the same nice feeling seeing those forks just fitting under the pallet. High precision farming requires path tracking in the order of centimeters. This accuracy can be achieved thanks to our feed-forward feature, which uses the path orientation information to compute ahead the necessary turning commands in non-straight paths. Finally, safety is very important in real-world applications, even if someone attempts to do something crazy and dangerous around this heavy tractor. Is the danger gone? Let's go back to work. Thanks for watching.
Hi everyone. In my project Dynamic Octomap, we try to solve the problem of building 3D map of static regions of the world. But we cannot simply take the difference in consecutive sensor measurements, as this can be either due to dynamic activity or sensor noise. But let us be clear, why does the problem matter? The knowledge of static and dynamic regions can greatly benefit while planning around the world. The existing work use an assortment of sophisticated techniques, but they have the same limitation. They represent the world as a point cloud map. The point cloud is severely space inefficient compared to the octomap. The octomap represents the world in octary format. This large chunk of unoccupied space contains the same data as a small region of unoccupied space, as shown in the right. This is achieved via tree pruning, which significantly reduces the data storage. But using only octomap is not enough. In the left pane, we have a patrolling agent in gazebo. In the right pane, octomap is unable to clear the cells at the center. Let's look at a solution. In the left pane again, we have a patrolling agent which translates and spins. In the center, we try to build an occupancy map of only the static regions. And on the right, we try to indicate all the dynamic regions in the world. We're able to see that the octa map at the center is able to build a pretty good map of the static regions. For more project information, please visit the project page.
Hello, ROS community. We want to share a new runtime environment for embedded systems. The code name is MROS2. MROS2 realizes pub-sub communication on embedded systems without agents. So we can now connect embedded nodes and native ROS2 nodes directly via topic. We offer a basic API library that is partially compliant with RCLCPP. For DDS, we employ embedded RTPS developed by RWTH Aachen University under MIT license. Embedded RTPS has interoperability with the first DDS by portable implementation of RTPS protocol. We provide reference implementation of MROS2 application with STM Nucleo F767 board and Topaz SP3 kernel. Here is a simple example code of MROS2 application. Embedded node will subscribe string message and publish it as is. You can see the MROS2 API is very similar to RCLCPP. Let's go to demonstration time. This demo consists of Foxy on Raspberry Pi 4, Nothing on laptop PC, and MROS2 on STM board. Foxy node will publish message to 2 STM topic, and Nothing node will subscribe message from 2 Linux topic. MROS2 node will relay this communication. So please check out our repository on GitHub and give us your star and contribution if you are interested in our activity.
Here we go.
At Trimble, we are leveraging ROS as a framework for building a versatile autonomy stack for off-road applications. The use of ROS enables us to readily assemble components to deliver bespoke solutions for specific applications. For the agriculture sector, this is an example of LiDAR navigation in an orchard running under ROS. This is our autonomous sprayer, where ROS is used to connect our safety, perception, path planning, and vehicle controller modules. The perception function shown here is detecting grain silos. ROS also connects to our internal simulator engine, the virtual proving ground. In the horizontal construction space, we can use the same perception functionalities, but swap in a different path planner and controller to enable autonomous compacting. Aside from solution delivery, ROS has allowed us to easily evaluate the pairing of our navigation and perception modules with sensors from different suppliers. Furthermore, ROS has allowed us to work more closely with our university partners. One noteworthy example is the integration of our LiDAR localization package into the stacks of the top 2 teams in the GM Auto Drive Challenge. If you found anything in this video interesting and would like to help us shape the future of construction, agriculture, and off-road autonomy, email us or reach out to one of our team members attending ROS World.
Hello, I'm Tyler Weaver from Picnic Robotics. At this time, ROS 2 is not nearly as mature as the old version of ROS. Ground-up rewrites always have this problem. That lack of maturity means it's much more likely in developing your project on top of ROS 2, you will encounter a bug or missing feature. What you do next is what I am here to talk to you about. Many of you are probably using ROS 2 Foxy. Can't really blame you that much, as we at Picnic were doing the same thing until recently. Best case, when you encounter a bug on Foxy, you'll try to create a PR to fix it. However, because you are on Foxy, your change cannot be accepted if you have to change the API. Secondly, as the people who are working on ROS 2 itself have very limited time to review external PRs, you're more likely to get your PR accepted if you target the latest version of that repo. Here's where you hit your next roadblock. The latest version of the ROS 2 repos is a large chain set away from Foxy. After all, Foxy's 1.5 years old. If you want to try to fix the issue in a way that can be upstreamed, you need to get your project to work on the latest API of ROS 2. There's a solution to that. That solution is to put your project on rolling. If you're working on rolling, fixing upstream issues is going to be much easier. I'm here to remind you why you started working on ROS 2 in the first place for your project. The big part of what makes open source software great is it's developed by a community of people that use that software. You should care about the software you depend on is healthy because it is part of your product. Have some long-term self-interest. Become a contributing member of this community for your own sake. Stop using old versions of ROS. Base your project on rolling, fix issues upstream, and come join us in advancing the frontier of robotics.
Hello, my name is Ryan Kim, and I developed an autonomously navigating mobile robot that tracks human faces, measures people's body temperature, and converses with them to help screen for COVID-19. Here is a video demonstration.
And checking for a fever. Please wear your mask and socially distance. Thank you. Hello, I am a mobile temperature scanner. I will be measuring your... May I ask you a few more questions about potential COVID-19 symptoms?
Yes.
Have you been vaccinated for COVID-19?
Not yet.
The 5 most common symptoms of COVID-19 are fevers or chills, coughing, shortness of breath or difficulty breathing, loss of taste or smell, and tiredness. Have you displayed 3 or more of these symptoms?
Yes.
These symptoms have been classified as the most common by the CDC and WHO. It is recommended that you get tested. Please wear your mask, socially distance, and consider quarantining yourself. Thank you.
Hello everyone, I'm Suhas, and today I will be presenting the latest release of Visual Circuit, which is a visual editor for robotic applications. I worked on this tool along with my mentors Josemaria Canas and Mohammad Taha Suhail during the Google Summer of Code. Visual Circuit provides a data-driven approach to build computer vision and robotic applications just by connecting different blocks with wires. We provide many OpenCV and ROS driver blocks for easy implementation. As an example, you can see in the image a simple face detection pipeline constructed using the camera, face detector, and screen blocks that are connected using wires. Regarding the architecture of Visual Circuit, it consists of a React-based frontend with a library of blocks. When a user designs an application and clicks on Build, a JSON config object is submitted to the Django backend, which bundles all these components to generate a Python application. To demonstrate the working of Visual Circuit, I will show an application where a quadcopter is made to follow along a road. In the application, data from a ROS camera is passed through many image processing blocks. A custom core block produces the error input for the two PID controllers and the output of which are used to drive the quadcopter. This design can then be built and downloaded as a zip file. After unzipping, it can be executed as a Python application. Coming to features, the latest release is a web-based tool which produces a single application package. All blocks execute in parallel and data is communicated efficiently using POSIX IPC. It has pre-built blocks for OpenCV, ROS and many more. To know more, please check out our website and also the GitHub repository. Thanks for watching.
Outdoor terrains. So if you want to navigate a robot in an unstructured outdoor terrain, how do you do that? That's what I asked myself when I started this project. So let's assume you're able to map this environment with point cloud. So you can use various 3D SLAM methods to build maps of such environments. And then you can use this point cloud map to measure traversability of local paths. After you have these traversability measures, you can then use this map to create a planning pipeline. Use this traversability to sample states and then use OMPL planners to create plans on top of these states. And then this basically becomes constrained planning problem. So we use OMPL planners to tackle the motion planning on unstructured terrain. And we perform a collision check with a 3D box that represents robot body and then an octomap that represents environment. So each state is validated by this collision check module. This is an example plan, and robot has already followed this plan through here. So this plan goes through an inclined hill, and then it gets into the final goal. This is another example of planning. So this is all in gazebo simulation. However, we also create a gazebo world from data that was captured from real world. And then we use this gazebo world to test and evaluate VoxNav. So this is another example navigation task where we give a navigation goal which is 60 meters away from the robot, and the robot here finds a path and then follows this path all the way to the goal. So there is about 2 meters of elevation variance on this navigation task. And the robot progresses here, and finally it reaches its goal with VoxNav. This is all components that composes VoxNav. So this video is too short to explain all of this, but this is good for reference. You can find the source code and documentation of VoxNav in the following links, and if you'd like to reach me, please do so. Thank you very much.
Hello, my name is Yuchen Wu, and I'm from the Autonomous Space Robotics Lab at the University of Toronto. In this short presentation, I'd like to introduce one of our recent projects, VTR3, that brings Visual Teach and Repeat into ROS2. So what is Visual Teach and Repeat? In short, Visual Teach and Repeat, or VTNR, is an end-to-end navigation framework for long-range and long-term path following in unstructured environments using only vision. With VTNR, the robot requires only a single demonstration of the path to follow, and is then able to repeat this path indefinitely across significant environment changes. And it's all achieved using just one camera, one laptop, and there's no GPS involved. So far, we have been working on VTNR for quite a few years and have successfully deployed VTNR on many ground and aerial vehicles. However, this won't be the whole story of VTNR, since there are still many interesting problems to solve, and we are really passionate about getting it running on more robots and in more diverse environments. So, starting last year, we have been developing what we consider as the third generation of Visual Teach and Repeat, that is now fully supporting ROS2 and with many new features coming as well, such as deep learned image features that's being more robust to lighting changes, and LiDAR and radar localization pipelines that expand VTNR beyond using only cameras. Well, early this year, we have already shared our codebase with our partner at Defense Research and Development Canada, DRDC, and had VTR3 tested on their Argo robot that is already ROS2 enabled. And now, we have made this entire project open source so that everyone can try it out on their own robots. Thank you for your attention, and please visit our website if you'd like to know more about VTR3.